I am Prakash NC, M.Tech in Computer Science and Engineering, second sem from PESIT. Today I am going to give seminar on RSA and Rabin-Karp algorithm. The agenda or outline of my topic is private key cryptography, public key cryptography, public key characteristics, public key cryptosystem, public key applications, digital signature, security of public key schemes, the RSA cryptosystem. These are all the topics which I am going to cover in this RSA algorithm. After that, we will see how Rabin-Karp algorithm helps in string matching. RSA algorithm. In traditionally, the people going to use only one key that will be shared by both sender and receiver, so that sender, whatever the intended message he has sent to the receiver, he can get the information. So the system, communication system is disclosed, so no need to worry about the message is leaked or someone hacked it, or not, no worry about that one. But as the day passes and the technology improving, we have seen so many drastic advanced applications where we placed in these crypto systems from past 300 years. Now we are going to use two keys. One is public key and another one is private key. Since because of we using a public key and as well as private key, the system is asymmetric. It uses clever application of number theory concepts to make the functions of both public key and private key concepts. As I told you, this system RSA algorithm uses two keys. One is public key and private key. Public key, as the name itself saying that this key known by everyone and can be shared with all other people, and mainly used to verify the signature and to encrypt the message from the plain text to ciphertext. Private key. Private key, as the name itself, that is private or solely belongs to only one person who is receiving the message, has to check the message, the intended message is whether it's in full format and what he expected message from his sender side. And this key also helps in the checking the method which is taken from the sender side, whether to say that is it received the full message or something wrong in that message, using decrypt the message. Here is an example. Bob wants to send the message to Alice, so he converts the plain text using the natural language. He converts that plain text to ciphertext using public key which is using. So that message will be sent to the Alice using some communication media. When Alice found that message from that Bob, he going to decrypt that message using his private key. That is exactly reverse of the encryption. After that, he going to read the plain text. Again, that after the decryption, Ali going to check what are the message the Bob has sent to him. This is how the message is conveyed to sender to receiver with a nice security, without worry about the message is leaked and someone hacked. It is developed to address the two key issues. One is key distribution, how to have a secure communication in general without having to trust some persons with your key. Digital signature, how to verify message comes intact from the claimed sender. Okay, whatever the message you sent, How are you going to know that the message you received, whether it is sent from that sender side, contained all the information, or that will be some modified message? Public key algorithm rely on two key with the characteristic, that is, one is it is computationally feasible to find the decryption key knowing only algorithm, and encryption key computationally easy to decrypt the message with the relevant information. This is how exactly the public key crypto system secrecy and authentication going to implement on this RSA algorithm. Source A and destination B. Source A wants to send a message to B, so you are going to convert the message using encryption algorithm. So the converted one is encryption algorithm, that is equal to Z, that will be given to the destination side. Destination person B decrypt that algorithm using Z. Later that you are going to decryption algorithm Y, and that plain text or whatever the information he has sent from the source A going to read by B. This is how that public key RSA algorithm going to work. We can classify this RSA algorithm into three categories. First is encryption or decryption, it's going to provide secrecy. Digital signature, it provides authentication. Key exchange, the session keys. Some algorithms are suitable for all users, others are specific to one. From these three categories, some of them can be used in all algorithms, and some of them applicable to only some feature. So digital authentication, Alice is going to do his authentication using the sign SA, secret key of Alice. So that will be the message M dash converted to digital signature, that will be sent to Bob. Bob going to verify using his public key from the Alice, and later that he is going to decide whether the digital signal is whether it is correct or wrong. Then only going to decide whether it is going to shall I going to accept or reject the message. This is how the explanation of the previous figure. Stands for secret key of Alice. Using that function and taking input M dash, I am going to send the message to Bob along with the message and as well as digital signature. Bob going to check using the public key of Alice to check whether that information sent by the Bob Alice are correct or not, along with the digital signature. If it is fine, then you are going to receive, or as well as you are going to discard the message and feel that something went wrong in transmission errors, or something as modified in that message. Digital signature provides both authentication of the signer's identity and authentication of the content. A digital signature must be verifiable by anyone who can access to the signer's public key. A signed message can be verified by one party and then passed on to other party who can also verify the signature. A signed message is not necessarily encrypted. The message can be in the clear and not protected from the disclosure. Like private key scheme, brute force exhaustive search attack is always theoretical possible, but key used are here from that brute force exhaustive algorithm. The key used are too large. Security mostly relies on large enough differences in difficulty between easy and hard problem. More generally, the hard problem is just made to hard to do in practice. It is hard. If something is the key is too large and it takes much time to do the authentication or encryption, so we consume that much language, much of our time. Requires the use of very large numbers, hence is now slow compared to private key scheme. Brute force the exhaustive search. So we'll see the procedure how the algorithm public key crypto system going to work. In first step, we're going to select a random two large number, that is P and Q, such that both P and Q are 1 KB bit. Compute n equals PQ, that is multiply those two numbers. Select a small odd integer e that is relatively prime to n, which is by equation equals P minus 1 into Q minus 1. Compute D as a decryption key as a multiplicative inverse of E modulo n. Guarantee that D exists and it is unique. As I said, it is decrypted. It is a secret key given to the receiver section. Publish the pair of both public key as well as decryption key as a participant's RSA public key. We are going to publish, but public key can be known to anyone, but decryption key should be known to only the intended or relevant receiver section. Keep the secret pair of both secret key and decryption key as a participant RSA secret key. So let us see how we are going to encrypt and how we are going to decrypt the messages. To encrypt a message, the sender has to do two things. Obtain the public key of the recipient using, as I said, using two numbers. You are going to multiply those two numbers and encrypt message. Compute the message mod n, where that message is not equal more than that computed P and Q. To decrypt the message, the receiver section know it is private key and he must know decryption key and both what are the information implemented in that private key. He is going to decrypt the message using the n. The message m must be smaller than the modulus n. It is the condition holds. So this is an example of RSA algorithm. We are going to solve based on the steps given to the RSA algorithm. Select two random numbers, prime number P and Q. Here it P is 7 and 17 and Q is 11. Compute P and Q, which is 187. Compute that pi, which is encrypted one, P minus 1 Q minus 1, which is 160. Relatively prime, that is only the GCD, which is equal to 1. Choose equal to 7. Determine the D 1 mod 160, which is D is less than 160. The value of small d, the decrypted key, is 23. Publish this key 7 and 187 and secret key as 23, 17 and 11. This is how the encryption and decryption of the following example going to give. The ciphertext is 11, that is encrypted one, and decrypted one is 88. Before going to implement or going to use this RSA algorithm, the sender and receiver has to follow some important sections here. First, those two members should know determine the two prime numbers randomly and select either E or D for encryption and for decryption and compute the other. Prime number p and q must not be easily derived from the modulus. What it means is it is sufficiently large and typically guess and use probability test. Exponent E, D are inverse, multiplicative inverse, so use inverse algorithm to compute the other. If we know E and we can compute D, and if we know D you can complete E. How that RSA algorithm going to attack? Brute force key search. It is infeasible given size of numbers. Mathematical attack based on the difficulty of computing pi of n, because if we take the large number multiplied by the result of p and q, so it is going to be the large number, so that we don't have much memory to store all the information. Timing attack because of running the decryption key. This is how all the things going to work. Now let us see what is Rabin-Karp algorithm and how going to work. The Rabin-Karp algorithm, in this seminar I am going to talk on. First is introduction, second one is computation of parameter with example, what are all the problem and how to solve this one, pseudo code of Rabin-Karp matcher, time complexity of Rabin-Karp algorithm. First let us see what is Rabin-Karp algorithm. Rabin and Karp proposed this algorithm, so the name is Rabin-Karp algorithm for string matching algorithm. It is generally used in all algorithms such as two-dimensional pattern matching. Now for example, we are going to all of us know the Google. When you are going to type, it will show that what are the in future, what are the information you have to send, and Google search, it shows so many options if you type some word. Rabin-Karp algorithm uses pi of n m pre-processing time, and in worst case running time it is pi of big theta of n minus m plus 1. In processing time it is big theta of m. This algorithm makes use of elementary number theoretic. So we will take one example how we are going to illustrate this Rabin-Karp algorithm. Let us take the input size from 0 to 9, so that the base of this 0 to 9 is decimal fraction, it is 10. So radix base or anyone is equal, and we will take d. Now in our example it is 10. I am going to derive the pattern from that input 0 to 9, which the derived pattern p, we are going to denote some value p which is correspond to decimal value, and the text pattern, let us take t as the decimal value that is derived from text pattern, which is the length of m. And if you are going to say that the decimal value from pattern string and text string are equal, if and only if when you are going to match and that in the text string and with the pattern string, that string exists in the text string. We can also compute the value of p using Horner's rule as shown in that equation. Similarly, t naught from that text string with the big theta of m. To compute all the remaining t1 to t till t minus n minus t of n minus m with the time big theta of n minus m, we can, using this algorithm, we can derive that t of s plus 1 using ts as a constant using this equation. The main problem is how we are going to derive that p and ts is too large to work with conveniently. So if T contains m character, then we cannot reasonably assume that each arithmetic operation on E takes constant time. It's obvious, right? When we take some characters, and if we take small characters, it will take less time, and if you choose large character of string some length, it will take much time. So we can compute p modulo q with big theta of m time and all its ts value modulo q in big theta of n minus m plus 1 time. That is the processing time. If we choose the modulo q as a prime such that it is 10q just fit within one computer world, then the algorithm works fine. The thing is, we need to choose the q value more carefully so that it gives a feasible time for us to compute the value of first match of the substring. As I told you, we must choose q, and solution, if it is that the value which is chosen from the text string and pattern string are equal, then it is value shift, and other it is not value shift, as showing the equation. Any shift yes for which both the text string is congruent to p mod q must be tested further. So it is whether yes is really valid or we just as spurious it. Rabin-Karp algorithm. This is an example of how. So we'll take some substring from the text string. It is pattern string is 31415 with the modulo q. That is, here the q value is 13. So when we compute this 31415 mod 13, we'll get a remainder of 7. So take the value of 5. Now the substring length is 5. So we're going to choose first 5 character of text string and we'll compute the remainder. So in the first 5 character will get 8 when made that value with mod 13. So like that we're going to follow. When we found that 31415, which is exactly the same as our chosen pattern string, that remainder is 7, though this is the valid match. And spurious hit, even though the text string and the pattern string is not equal, but remainder is showing that this is 7, so it is spurious hit. So this is how we're going to compute the value of remainder as well as using mod value, shifting from left to right or from right to left, and with the value. This is going to show that the new lower order digit shift, how many time you have to shift, how many position, and old higher order digit is going to show. So now we are seeing that Rabin-Karp pseudocode. The following procedure makes this idea precise. Rabin-Karp algorithm usually it takes 4 input. First is text string, pattern string, and D and Q value. Q value modulus and D value to decrypt that one, or to solve that one, what is D and how many bytes we have to shift. D is radix, as I said, a base. It is a base. The subscript and T are provided only for clarity. Subscripts. The program works correctly if all subscripts are dropped. Line 3. Now let us see how Rabin-Karp going to work. How it works. First, line 3 initialize H, higher order digital position in m digit window. Line from 48 compute the value of P such that it is pattern string. with the mod q and t naught as the value of text string with mod q. Mod q applicable to both pattern string and text string. We are going to compute the value from number 9 to 14 through all possible shift s, maintaining the following invariants, which is going to take the value ts. When p equals t in the 11th, it is an 8. It means we succeed in when we finding that pattern string in the text string. Line number 12 prints out the valid shift that are found, and if the shift less than that length of text string minus pattern string, then the for will execute at least one more time. If it is less, the shift is less than both n minus m difference, and the first execute to ensure that in the 14 line invariant world when we go back to line number 10. Line number 14 compute the value of the shift position with mod q from the value of ts mod q in constant time using equation directly. And with all these things, the time complexity of Rabin-Karp match algorithm is big theta of m for processing time, and for matching time big theta of n minus m plus 1 in the worst case. Since it is name string matching algorithm, since it is direct linear, the Rabin-Karp algorithm explicitly verify very valid shift. Thank you.